Hello and welcome to this lecture, students. Today we are going to discuss about the test pattern generation for combinational circuits. So in previous 2-3 lectures, in a couple of lectures, we discussed about the fault modeling of combinational circuits, the concepts of fault propagation, then fault detection, then how the test vectors can be generated. These things we already discussed. In today's lecture, our focus will be on how we can generate the test pattern to test any combinational circuit. Okay, so if we see the basics, if you are going to test any kind of circuit, what will be the input? The input will be the circuit netlist and a fault list F. Fault list F means there can be stuck at 0, stuck at 1, and open or short faults in case of the number of faults that we have already studied. Circuit netlist means what kind of circuit we are going to test. And what is the output? Output is a set of test vectors T to detect the faults in F. F here is the fault list. Now, and also a list of undetected faults. Suppose if any fault is remaining and if it is not detected, then a list of undetected faults. We can understand this particular theory by this diagram. Suppose this is a circuit which we are going to test. So what will be the input? Input will be the fault list. Fault list will sensitize the circuit. Okay, and accordingly the test vectors will be generated. So these test vectors are definitely dependent on these fault list. So if I am saying that I want to detect stuck at 0 fault in an adder, or suppose in any multiplexer, so accordingly I have to generate the test vector so that I can go back and test whether stuck at 0 fault is there or not. So input is the fault list and output is the test vector, and this test vector is responsible to generate the output for my testing. For example, here this is 3 input XOR gate, and if you see 4 lines are there, 3 are the input lines and 1 is the output line. How many possible combination of faults can be here? If I will talk about the stuck at 0 and stuck at 1 fault, then there can be 8 combination. Each of the line can have stuck at 0 fault or stuck at 1 fault. So if you just multiply, we will get 8. I have already told you in previous lecture as well. So to test this particular XOR gate, we require only 2 test vectors, that is 0, 0, 0 or 1, 1, 1. And by these 2 test vectors, I can, test any of the 8 faults that can occur in this particular XOR gate. How that you go and see in the previous lecture. Okay, in previous lecture I have covered in detail that for NAND gate, for AND gate, for OR gate, for XOR gate, how many test vectors are required and how we can decide the test vectors. Okay, so this is not the topic of this lecture. You can go back and see in the previous lecture how we can decide the test vectors. Okay, now what is the motivation behind test pattern generation? Now, drastic reduction in the number of required test vectors compared to the naive approach. So compared to the approach that is not advanced, or we can say that is at the initial stage or the conventional approach, the test vectors are such that they are very small in numbers. How that we can see here. 4 input AND gate. Suppose I want to test 4 input AND gate, then it will need only 5 vectors. 0, 111, 1011, 1101, 1110, 1111. So using these 5 vectors, I can test any 4 input AND gate. Similarly, if I will talk about 5 input XOR gate, only 2 test vectors are needed, that is 0, 0, 0, 0 and 1, 1, 1, 1, 1. Isn't it? So by using 5 test vectors, I can test 4 input AND gate, and by using just 2 test vectors, I can easily test 5 input XOR gate. I will again repeat how these test vectors are coming here. This 0, 1, 1, 1, 1, 0, 1, 1. and this 0 0 0 and 1 1 1. You can go back and see in the previous lecture when I explained you about the test vectors for and OR gate, XOR gate, and NAND. Okay, then you will definitely understand this. So if I talk about the binary logic, then if a 4 input AND gate has to be tested, it will require 2 to the power 4 equals to 16 different test sequence or different test patterns. And if I talk about 5 input XOR gate, it will require 2 to the power 5 equals to 32 different combinations to test that particular XOR gate. But here we can see that only 2 test vectors are required, and here we can see only 5 test vectors are required. So you can see that there is a drastic reduction in number of required test vectors when we compare it to the naive approach. Okay, so this is the motivation behind it. Now see here, this is just an example to since we are going into the test pattern generation topic. So before that, I am just explaining one example over here. This is one OR gate, AND gate, and AND gate. How many lines are there? Let us count. 1, 2, 3, 4, 5, 6, 7. 7 lines are there. Lines means interconnections. 4 inputs are here. This is the 2 intermediate connection, 4 plus 2 6, and 1 output 7. This is how we count the lines. So 7 lines are there. Since 7 lines are there, 14 stuck at 0 or stuck at 1 faults can occur. Each line can have stuck at 0 or stuck at 1 fault. Okay. Now see here. The test vector is 1 0 1 1. What is the test vector? 1 0 1 1. Let us apply here. 1 0 1 1. This is 0, this is 1, this is 0, so the output will be 1 here. This is 1, this is 1, so output will be 1 here. Since both the inputs are 1 for this AND gate, the output will be 1. Now using this test vector, how many faults we can test? So we can test A stuck at 0, we can test C stuck at 0, we can test D stuck at 0, we can test F stuck at 0, we can test G stuck at 0, and we can also test E stuck at 0. How we can test this particular faults, this also I already told you in the previous lecture, but for your sake of understanding in this moment, I will just explain about this 1011 and about all these faults that we can test. So A is stuck at 0. So if A will be by any of the means or by any of the fault, if A is stuck at 0, since we are applying the logic 1 here and we are saying that A is stuck at 0. So if A is stuck at 0, then what will be the output of this OR gate? If A is stuck at 0, 0, 0 will give you 0. Is it not? And what we are applying at the test vector, we are applying it as 1. So you can understand that the original logic is not matching with the faulty logic. Here the output is 1, and if fault is there as stuck at 0, then you will be getting the output as 0. So original output is 1 and the faulty output is 0. So again, the test vector ZT is in XOR condition with the fault T, ZF of T. So if there is any difference between the original output and the faulty output, the fault will be detected. And this is how we can also see C stuck at 0. You can see C is stuck at 0 because if this is 0, then this will also be 0, and originally it is 1. Is it not? Similarly, you can also test D stuck at 0. Similarly, you can also test F stuck at 0. Similarly, you can also test G stuck at 0, and similarly you can also test the E stuck at 0 by following the same logic. Okay, so this is how by applying these particular test vectors 1, 2, 3, 4, 5, we have applied only 5 test vectors and we are testing how many faults? 14 faults. Okay, so these test vectors you can apply in this particular circuit, and you can see that these test vectors are fulfilling the criteria or not. That is your part, that is your you can say the assignment that you can do and practice about understanding this particular test vectors. Okay, so just for example, I have told you this particular thing, and by this we can move to the next I would say this necessary condition I already told you. If the the original test response is not matching with the faulty test response, then this condition will be true and the fault will be detected, as I already told you number of times earlier as well. So this is just an example to understand the test vectors and not the method to generate the test pattern. Do not confuse by this example. This example is just telling us how we can test the particular faults by respective test vectors. But this is not the method to generate the test vectors. Okay. So what is the method then to generate the test vectors? So the conventional method, or we can say the first method, is generating test pattern from truth table. Generating test pattern from truth table is the first method that we are going to study. How to generate test for the stuck at 0, that is fault alpha. So stuck at 0 fault alpha. Here I forgot to draw. Here is the fault. The fault is here, and we want to select. We want to set the test pattern, or we want to generate the test pattern for this particular fault. Fault is here, in this line, in this particular line. So this is my input. These are my inputs A, B, and C, and this is fault free condition, and this is faulty condition. Okay, let us see how this truth table is generated first. So what is the function of this truth table? If we can quickly review this, this is the AND gate, so the output is AB, and this is the AND gate again. So first input is connected with A, so the output is AC, and this is OR gate, so my function will be AB plus AC. Okay, so AB plus AC, accordingly you can generate the output F. So if I am applied 0 0 0, if I am applying 0 here, 0 here, 0 here, put A as 0, B as 0, A as 0, and C as 0, you will get 0. And similarly so on, 0 0 0, again I mean A as 0, B as 0, A as 0, and again C as 1. And similarly, by applying different inputs, you will get these fault free outputs. You will get these fault free outputs. Okay, now I have to see, and this is the assumption that fault is there. This is the assumption that fault is there. So how will you check whether the fault is there or not? How we can check? We can check if there is fault or not by examining the difference between the faulty output and the fault free output. So what is here? 0 0 0 0 0 0 0 0 0 0 1 1, but here it is 1 0. Here it is 1 0. So this is the faulty condition. This is the faulty condition, and by applying our logic that ZT XOR with Z of FT means original and faulty response, or we can say the fault free and the faulty response, the XOR condition has to match. So here it is meeting. F is the fault free and F alpha is the faulty, and if we can easily see the difference between these two logics, I will say that the fault is in this particular logic or this particular. So this is how we can detect the fault in case of the truth table. But here I am talking about the very small function AB plus AC. What about the functions in the combinational circuit which has large number of inputs? Here we are talking about 3 inputs only, A, B, and C. But what if the number of inputs are 30? What if the number of inputs are 30? So the combination, the possible number of combination, or we can say the possible number of lines in the truth table will be approximately 1 billion. So can you generate 1 billion steps, and you can trace in every line that where the fault lies? Okay, so this is the impractical approach. This is the impractical approach. The truth table approach is impractical approach. Though you can generate the test pattern here also. What is the test pattern? Test pattern is 110. If you apply 110, you can see the difference between F and F alpha. So this is the test pattern for me, 110. So what I'm saying is, so though the truth table model is easy for understanding, but it cannot be applied to test larger circuit. So if you have larger circuit, you cannot go by the method of truth table. Then how we can do that? So that the next method is method of Boolean differences. And next method is method of Boolean difference, and what it will say. This is an algebraic method to generate all the possible test vectors to detect a given fault. Boolean difference is an algebraic method, and by this method we can detect, or we can generate number of test vectors to detect any given fault. It is simple in concept but difficult to automate. Concept is simple but automation is difficult. We will see. Next is the Boolean difference of a function. Let us say function comprises of x1, x2, xn. With respect to one of its variable xi is defined as. Again, I am repeating, the Boolean difference of a function f with respect to one of its variable xi is defined as df upon d of xi. It is a derivative kind of approach. So what I am doing here, I am taking one function f x1, xi minus 1, 0, xi plus 1 and so on xn. We are XORing it with the next function which has the value 1 here. So let us say this is fi0 and this is fi1. So the XORing will be here. Okay. So it means that the simple meaning is that you first set in a function xi equal to 0. I am setting the function xi equal to 0 here, and then you set xi equals to 1, and then see what will be the function look alike, how the function will look alike. So definitely if you are setting xi equal to 0, the function looks different than if you set xi equals to 1. Then we have to see what is the difference between this function and this function, and whatever may be the difference, if there will be any difference, that will be detected using this XORing condition. Okay, so the Boolean difference method works like this. Okay, so the Boolean difference df upon dxi specifies the condition under which any change in line xi will propagate to the output. So if any change will be there, it will definitely propagate to the output and we can detect the fault. So what are the necessary and sufficient conditions to detect a fault xi? C here is stuck at 0, or either it can be 0 or either it can be 1. So we can write xi is stuck at 0 or xi is stuck at 1. Okay, so what are the necessary conditions so that we can go ahead with this particular method? First is a reverse logic value c bar must be applied to xi to excite the fault. I am repeating, a reverse logic value c bar must be applied to xi to excite the fault. Okay, line xi will have different values in fault free and faulty circuits. Let us understand this with this example. Suppose I am saying about this, I am talking about this 2 input AND gate, and I am saying that this particular input is stuck at 0. So if you want to sensitize, or if you want to generate the test vector for this particular logic, then you have to apply the reverse logic here. Then only you can see the difference. How we can understand this? Suppose this is logic 0. I mean this particular line is stuck at 0. Since this is AND gate, you will always get the output as 0 because this is stuck at 0. Now what I am saying, I am saying that I have to apply the reverse logic. So if I am applying the reverse logic here, what is the reverse logic of 0? It will be 1. It will be 1. So definitely the output will differ. Definitely the output will differ, but provided this line should be, uh, this line should be uncontrollable line. I will discuss the logic of uncontrollable line in the next couple of minutes. But here I would say that if you want to test any logic or any fault at any given line, that you have to apply the reverse logic to test that particular fault. Okay. Now the change on line xi must be propagated to the outputs. Whatever change this line will have, that has to be propagated to the output. If you don't propagate the change to the output, then you cannot test that particular fault. These are the two necessary and important conditions, sufficient condition to go by the method of Boolean difference. Okay, so now what is how we can summarize this. So first point is the set of test vectors that can detect the fault xi is stuck at 0 is given by xi df upon dxi equals to 1. If this condition is true, then we can test the stacked fault at 0. And the set of test vectors that can detect the fault xi stacked at 1 is given by xi bar. Why I am taking xi bar? Here what I am testing? Xi stacked at 0. And what logic we are applying? The reverse logic. Xi means 1. And what is the fault? Xi stacked at 0. So 0, and here we are applying the reverse logic 1. And here xi is stuck at 1, and I am applying the logic xi bar, means I am applying the logic 0. So the first condition is, what is the first condition? You have to apply the reverse logic in order to excite the fault xi. So I am applying the reverse logic. In case of stuck at 0, we are applying xi, and in case of stuck at 1, we are applying the xi bar. Okay, so this has to be, give the value as a true. Here 1 means not the multiplication of this particular thing, 1 means the true condition. If these two conditions are meeting, the fault difference is meeting with this condition 1, then we can say that fault can be detected. Okay, this is one of the method. Now next method is test generation using path sensitization. This method is very important, and it is the basic of all automated test pattern generation scheme. Okay, so we are going to study this and we are going to understand this. Similar in concept to Boolean difference, in the sense that we excite the fault and then propagate the fault effects. But what are the differences? Boolean difference works from function separation. Path sensitization directly works with circuit netlist. So Boolean difference, we are talking about the functions expression. Here we have talked about the expression of the function. This is the function 1 and this is the function 2. But here in case of the path sensitization, we will talk about the circuit itself. We are not going into the function. We are talking about the circuit netlist. We are talking about the input and output of the gates. Okay, so if there is any fault in input and output of the gates, it should be propagated to the output, and accordingly the test vectors must be sensitized to detect that output. So here in case of the Boolean difference, you have to have the function expression, and by by understanding the difference in the function, you will detect the fault. But here in path sensitization, it is more realistic approach. It is more practical approach. Why? Because we will directly talk about the path that is connected between these two particular gates. So if I am talking about this particular error or particular fault alpha, I am talking about this particular line. So this is how when we go for the structural level test, the path sensitization gives you the more correct logic or more appropriate logic, and it is easy to understand as well, and it is the basic of the automated test pattern generation schemes. Okay, so next is to propagate change in a gate input to the output. The other inputs must be set to the corresponding non-controlling value. I told you in the previous page about the non-controlling value that we are going to see. What is non-controlling value? Now see, there is stuck at 0 or stuck at 1 fault here. Suppose I assume that this alpha is stuck at 0. So in order to propagate this particular fault here, because I am saying that the path sensitization method, the first requirement is whatever fault is here, that has to be propagated to the primary output. So what should we apply here? What should we apply here so that it will not affect the output over here? If it is 0, the f will be permanently 1. If it is 0, then f will be permanently 1. Why? Because this is NAND gate. So if we apply here 0, whatever may be the fault, stuck at 0 or stuck at 1, we are not talking about that. Whatever may be the fault, this f will always permanently will be set to 1 because of this property of the NAND gate. So the correct logic here is to apply 1. How? Let us see by the example. Suppose this line is stuck at 0. So what logic will come here? 0, and this is 1. So 1 0 will give you the output as 1. Similarly, if the stuck at 1 fault is here, and if you are saying that this is 1, then 1 1 will give you output as 0. So accordingly, you will set the test pattern over here. Accordingly, you will set the test pattern over here and here also, because this 1 is not affecting the output. Whereas if we apply 0 here, it will permanently become 1. It will not change. But in case of the input as a 1, the output is changing with respect to this particular fault. I hope you are getting. So in case of the NAND gate, we should apply here 1, and this 1 is nothing but the non-controlling value or uncontrolling value. Not uncontrolling value. Uncontrolling value will be wrong to say. It is non-controlling value. So if we talk about the AND gate, OR gate and XOR gate, for AND gate the non-controlling value is 1, for OR gate the non-controlling value is 0, and for XOR gate also the non-controlling value will be 0. So if we talk about AND gate and NAND gate, the non-controlling value is 1, and if we talk about OR gate and XOR gate, the non-controlling value is 0. Okay, now I want to make you understand this by one simple example. If you have studied all the digital electronics in your B.Tech, then you might have studied about the inherent property of AND and OR gate. What is the inherent property of AND and OR gate? How OR gate behaves? If both the inputs of OR gate are set to 1, you will always get the output as 1. And if any of the input is set to 1, you will always get the output as 1. So what does it mean? OR gate is sensitive to logic 1. OR gate is sensitive to logic 1. So if I am saying that I want non-controlling value, and if I am applying 1, so can 1 will be the non-controlling value? Never for OR gate, because if any of the input is 1, you will always get the logic as 1. So since OR gate is sensitive to 1, we cannot apply 1 as the non-controlling value. So what is the non-controlling value in case of the OR gate? Is 0. Now come to AND gate. If any of the input of the AND gate is 0, you will always get the output as 0. So AND gate is sensitive to 0. So can it be non-controlling value? Never, because you apply 0 here, you will always get the output as 0. So what is the non-controlling value in case of the AND gate? It has to be 1. So this is how we can understand the concept of non-controlling value. Okay, so what is the basic principle behind the path sensitization? At the site of the fault, assign a logic value that is complementary or reverse to the polarity of the fault being tested. Explained already in the previous page. Second, for forward drive phase. What is the forward drive phase? Select a path from the site of the fault to one of the circuit's output, that is the primary output, because we have to propagate the output. We have to propagate the fault. Okay, and then sensitize the path by assigning non-controlling values to the inputs of the gates along the path so as to propagate the effect of the fault, that we have already seen in the previous page. We will see one example, then you will surely understand this thing. Now the third step and the important step is backward trace phase. Okay, what is the backward trace phase? Determine the primary inputs that will produce the necessary signal values as specified in step 1 and step 2. So above two steps have to be followed by the third step, and in third step we will ensure that there will be no fault in the propagation of the signals from input to output. Okay, so by backward tracing we can ensure that. So it requires tracking the signals back towards the primary inputs. It requires tracking the signal back towards the primary input. Okay, so whatever we have seen in the these three steps, that we will apply in this particular example, so that you can easily understand what is the forward and backward tracing and how we can decide the test vectors in case of the path sensitization method. Okay, so see this example here. This is one OR gate, this is AND gate, this is OR gate, this is NOT gate, and this is AND gate. What we are doing, we are going to test the stacket 1 fault at this particular path E. I am repeating, this example is for stuck at 1 fault at this particular path E. Now see, what is the first step? First step is, at the site of the fault, assign a logic value that is complementary to the polarity of the fault being tested. So what is the polarity here? I am talking about stuck at 1 fault. So at here we have to apply the logic 0. This is the first thing that we have to do. Now, what is the next step? That is the forward tracing. Select a path from the site of the fault to one of the circuit output. Okay. And then sensitize the path by assigning non-controlling values to the input of the gates along with the path so as to propagate the effect of the fault. Now here the path will be, one of the path will be here, we can say the H, and through H it will go to the primary output Z. So I am selecting this path, and this has to be the path because there is no alternative available over here in this particular diagram. So if I have to propagate this fault to Z, I have to follow from E to H and H to Z. So if I want to propagate this particular logic 0 over here and then here, so what I will do, I will make the uncontrollable value of this AND gate. And what is the logic for uncontrollable value or non-controlling input for the AND gate? It is 1. And for OR gate, it is 0. We have seen in the previous page as well. There is nothing new about this. So what is fixed? What is fixed? 0, 1, and the whatever may be the fault that will be propagated to H. And here it is 0, and whatever will be the fault, it is propagated to Z. Okay, so by this logic, this is known as the forward tracking. This is known as the forward tracing. So now I have told you about the forward tracing. Let us see what is backward tracing. We are not knowing, we have set the logic for E, we have set the logic for F, we have set the logic for 0, but we are not knowing what should be the input of A, B, C and D. So how we will assign input for A, B, C and D? This is known as the backward tracing. Let us see. So if this has to be 0 to test the stuck at 1 fault, here the two inputs A and B has to be 0 because this is an OR gate. If this is 1, then C1 has to be 0. And if this is 0, then C has to be 0. Okay, we have already talked about the logic here. Okay, so irrespective of D, if I am setting C, the output will always be 0, and this is satisfying my condition. So what is the test vector we have determined? We have determined it as 0, 0, 0 and don't care because D is not affecting my logic. D can be anything because we have set C as 0. Because C is 0, whatever may be D, the output will always be 0. So D is my don't care. So 0, 0, 0 and don't care will be my test vector. And how this has come into existence? Because we have backward traced the logic from output to input. So this is known as the backward tracing. Okay, so we have applied the logic. First we have applied the reverse logic, then we have seen that how this reverse logic can be propagated to Z, and accordingly we have set 1 and 0 here, and then we have done the back tracing by applying the the implications. These are the implications. This has to be 0, this has to be 1, and by knowing this particular logics, we have set the A, B, C and D and decided the test vector for this particular combinational circuit. So this is how we have decided the test vector, and I hope you have understood. We will see some other examples when we will talk about the automated test pattern generation scheme, and then you will definitely understand some more examples on this. So what are the points to note here? Path sensitization is not as simple as the example shows. Okay, so there can be conflicts while backtracking, and then more than one path may need to be sensitized. Yeah, so what is that particular point is saying? Suppose you are backtracking from here to here. It may be possible that you are applying logic 0 and here you have to say you have to apply logic 1 here, or you are applying here 1 and you have to set logic 1 here or 0 here. So depending upon some conflicts may be there. because you are back tracing from Z to A, Z to B, and from output to input. So the conflicts can be there, and you have to sensitize more than one path. Okay, so these are the difficulties of path sensitization method. So more sophisticated ATBG tools are available for combinational circuits nowadays. More, advanced and more sophisticated tools are available. But yeah, the another point which is important to remember here, the path sensitization method is the basic of all automated test pattern generation scheme. Okay, so we will see automated test pattern generation scheme in the next lecture, and then we will talk about some algorithm, and in that particular algorithm I will tell you more detail about the path sensitization and the other algorithms that has been developed for automated test pattern generation scheme. Thank you for listening and watching this particular lecture.